We're back with another lesson provided by the Center for People Who Can't Math Good and want to learn to do other stuff good too. Today is all about actually proving theorems. We talked last time about logic, the thing that everybody thinks they have until they realize their most trusted foundation of understanding is based on a set of axioms that we still have yet to confirm are actually consistent. Regardless, we press forward on the frontier of knowledge, because we really have nothing better to do with our time as humans. The semester's been rough on you. Your 6-week summer course in proofwriting has turned into your worst nightmare, and you're suddenly finding yourself at church more often because you need some way to cleanse yourself from the Lovecraftian imagery that haunts your dreams. This is where I come in to help, and remind you that the more math you study, the worse it gets. Hopefully you can at least get your homework done with some guidance from a disembodied voice on the internet. Proofwriting is about crafting an argument to prove theorems, which are just important mathematical statements. It's about following a series of logical steps and reaching a conclusion without ambiguity for how we got there. If you claim something in mathematics, you have to prove it. Let's consider an example. I claim that if n is odd, then n squared is odd. If you're not sure how to proceed, start writing some examples. Suppose n is 3, which is an odd number, then n squared is 9. If n is 7, then n squared is 49. This seems to be good evidence that the claim is true. However, this is not a proof. How do you know? Is there an odd number, when squared, that yields an even number? The odds may have a double agent, trying to lull us into comfort until it attempts to break math. How do we know? To prove this directly, we have to generalize what an odd number is, and use that generalized form to prove something about all odd numbers. Odds are defined to be any integer of the form 2a plus 1, where a is an integer. So n equals 2a plus 1. If we square 2a plus 1, then we get 2a plus 1, the quantity squared, which is equal to 4a squared plus 4a plus 1. If we factor 2 from the first two terms, we have 2 times the quantity, 2a squared plus 2a, and then plus 1. We know 2a squared plus 2a must be some number, so let it be q. Then n squared is equal to 2q plus 1. That looks like an odd number to me. So we've come to our conclusion. This is an example of a direct proof, with a statement of the form p implies q. But there are more subtle and indirect ways of proving theorems that mathematicians have discovered. This involves logical equivalencies. Basically, these are the cheat codes that make math people seem way more clever and eccentric than they ever needed to be. And so math people are weird, and it's something to embrace, because otherwise we'd have to admit we aren't superior to engineers and scientists, and we can't have that. If P implies Q, an equivalent statement is not Q implies not P. For example, if I drink too much Monster, I will summon the spirit of Kyle and punch a hole in the wall. If I don't punch a hole in the wall, then I didn't have too much Monster. This is known as the contrapositive of the statement. Let's apply this to the claim from before. If n is odd, then n squared is odd. The contrapositive is that if n squared is even, then n must be even. If n squared is even, then n squared equals 2a for some integer a. If we divide by 2, then n times n divided by 2 is equal to a. This means that 2 must divide n, since a must be an integer. Therefore, n is even. This proves the original statement. So now we've proven the theorem in 2 different ways. Wowzers. Now that you have a basic understanding of what mathematicians go through on a semi-regular basis, you can take your newbie gains and flex on all your non-math friends. Do you even math, bro? The answer is calm down. You're not that cool because you know how facts work. Another proof technique involves negation. Suppose you have a statement P. Assume instead not P. If you're able to find a contradiction in the negation, then that means the negation is false, and hence the original statement is true. For an example, the time-tested overrated milestone of mathematical prowess is proving the square root of 2 is rational. To prove this fact, you may assume the square root of 2 is rational and try to find some contradiction, usually something that directly contradicts an assumption. Here's the proof. I'm sorry, did you want a real proof? Well, unfortunately for you, textbook authors are a lazy bunch. Oh well. Here's a small compilation of instances where authors decided not to bother. The last proof technique I want to cover is proofs using cases. This is the least elegant of the proof strategies, but it's significant nonetheless. One of the most trivial sounding statements of all time decided it would beat up mathematicians for a few centuries, take their grant money, shake them down until their souls embodied the literal abstraction of truth, and they finally said, let's get a computer to solve this. The computer exhausted all the possible cases to finally show Any map can be colored with 4 colors without there being adjacent colors. Consider the much less demanding example. If n is an integer, prove n squared minus 5n plus 7 is odd. To prove this, let's consider 2 cases. One case where n is even, another when n is odd. If n is even, n equals 2a. Substituting for n, we get 2a the quantity squared minus 5 times the quantity 2a plus 7. This is 4a squared minus 10a plus 7, which equals 4a squared minus 10a plus 6 plus 1. Factoring 2 from the first 3 terms, we get 2 times the quantity 2 times a squared minus 5a plus 3, and then plus 1. Letting q equal 2a squared minus 5a plus 3, n squared minus 5n plus 7 is of the form 2q plus 1 and is odd. If n is odd, n equals 2a plus 1. Then we have the quantity 2a plus 1 squared minus 5 times 2a plus 1 plus 7, which expands to 4a squared plus 4a plus 1 minus 10a minus 5 plus 7. This can be rearranged as 4a squared minus 6a plus 3. Furthermore, we can parse 3 into 2 plus 1 and factor 2 from all the terms but 1. We get 2 times the quantity 2a squared minus 3a plus 1, and then plus 1. Let q be 2a squared minus 3a plus 1, and we have 2q plus 1. This is odd, and once again, n squared minus 5n plus 7 is odd. Proving theorems is an involved process. We learn best through failure, or at least that's what keeps me going. The only thing a mathematician loves more than math is proving other mathematicians wrong. So be prepared to face the absolute wall of criticism that will follow every theorem you prove. You made it to the end. Thanks for taking the time to watch. If you liked the video, please share it, like it, and subscribe to get notified of more content. Every bit counts, so thanks.